Hello everyone, my name is Sandeep R. I am working as Associate Professor in the Department of ECE, Vidyavardhaka College of Engineering, Mysuru. In the previous video, we saw that when a complex exponential e power st is applied as an input to an LTI system, the output is also e power st with its coefficient being h of s. Similarly, when e power j omega t is also applied as an input, we get the output as h of j omega into e power j omega t. So that is, we get back the input in the output with its only change in its coefficient. That's the one thing we had learned. And also we had learned that by applying Laplace transform and h of t, that is impulse response of a continuous time LTI system, we get h of s, system transfer function. By applying for continuous time Fourier transform on impulse response h of t, we get h of j omega, which is nothing but the frequency response of an LTI system. And we said for Laplace transform is generic and Fourier transform is special case. Fourier transform is applicable only for converging functions, whereas Laplace transform can be applicable for both converging and diverging, but it exists only for specific values of s, and that is called as region of convergence. We will see, do we have similar kind of analogy for discrete time LTI system? So let us consider a discrete time LTI system with input x of n and output y of n, and impulse response is given by h of n. Let us consider a complex exponential, a discrete time complex exponential sequence z power n as an input, where z is equal to r into e power j omega is applied to LTI system. Since we know the impulse response of the LTI system, we can write the output using convolution sum as y of n is equal to summation k is equal to minus infinity to plus infinity h of k into x of n minus k. So since x of n is equal to z power n, I can write x of n minus k as z power n minus k. So summation k is equal to minus infinity to plus infinity h of k into z power n minus k. Using loss of indices, I can write this as z power n into z power minus k. I am summing up with respect to variable k, so it is independent of n, so I can write z power n as outside. So writing z power n as outside and summation k is equal to minus infinity to plus infinity h of k into z power minus k. Now this entire thing I'll call it as h of z, and here it is z power n. So you can see that if the input is z power n, the output is also z power n into h of z. That means what? So if z power n is applied as an input to an LTI system, we get the same z power n as an output with its only change in its coefficient, which is given by h of z. h of z is called the system transfer function of a discrete time LTI system, and here it is written as summation n is equal to minus infinity to plus infinity h of n into z power minus n. Earlier I had written in terms of k, now I am writing in terms of n because that was just a dummy variable. So what is the right hand side? Right hand side is a z transform of h of n, and left hand side is system transfer function of a discrete time LTI system. If the equation holds good for a sequence or a function h of n, it should in general hold good for any other function. So writing it as x of z is equal to summation n is equal to minus infinity to plus infinity x of n into z power minus n. So this is the definition for bilateral z transform of x of n. It is represented as x of z. We know that z is equal to r into e power j omega n, right? So since we know that z is equal to r into e power j omega, and making r is equal to 1, we get z is equal to e power j omega. Substituting that in the above equation, I can write, so h of e power j omega is equal to summation n is equal to minus infinity to plus infinity h of n into e power minus j omega n. Okay, because z is equal to e power j omega. What is this? This is right hand side is nothing but discrete time Fourier transform of h of n, and left side is h of e power j omega. This is called as the frequency response of a discrete time LTI system. So what I am trying to tell is, if h of n is there and if I apply z transform, then I get h of z, which is nothing but the system transfer function of a discrete time LTI system. H of n is there. If I apply discrete time Fourier transform, then I will get the h of e power j omega, which is nothing but the frequency response of a discrete time LTI system. Now, to be specific, z transform is generic. Z transform is applicable for both converging functions as well as diverging functions, but whereas the discrete time Fourier transform is applicable only for the converging functions, that is only if it is absolutely summable. Why is z transform so special? If you look at the definition, say x of z is equal to summation n is equal to minus infinity to plus infinity x of n into z power minus n. Now, say suppose I consider a discrete time sequence, say x of n, and it is say exponentially growing. So let us consider that. So it is growing. So as n increases, it is becoming it is a diverging function. Now okay, so for this case, discrete time Fourier transform does not exist because it's a diverging function. Now let us, if you observe that we are multiplying that with z power minus n. So multiplying with, it's a complex exponential sequence. So if I take care that this is multiplied with z power minus n, which decays at a rate faster than which x of n is growing. So if I make sure that this decays at a faster rate, okay, and now I am multiplying these two functions, the resultant I will get a function which will absolutely be summable, and hence the z transform exists. Now what is deciding that the z transform is existing? That is the value of z, because only the z will decide the rate at which it decays compared to the function of x of n. So that is why z transform exists for both converging and diverging, but for specific values of z. The range of values of z for which the z transform exists is called as the region of convergence. Region of convergence. Okay. Now, okay. So now we have seen the similar analogy in the continuous time LTI system. Now here we can say that z power n is an eigenfunction of discrete time LTI system. Z power n is an eigenfunction of discrete time LTI system, and also e power j omega n. E power j omega n is also the eigenfunction of LTI system, and then for specific value h of z is called as the eigenvalue of, for specific values of z it's called as eigenvalue of LTI system, and similarly h of e power j omega is also called as the eigenvalue of this LTI system for specific values of omega. Okay, now summarizing it, so if z power n is given as an input, I get back the same z power n as an output with its only change in its coefficient, which is nothing but h of z. H of z is called the system transfer function, which is obtained by applying z transform on h of n. If I apply discrete time Fourier transform on h of n, I get h of e power j omega, which is nothing but the frequency response of LTI system. And the other thing is z transform is generic, whereas discrete time Fourier transform is specific case. Discrete time Fourier transform is applicable only for converging functions, whereas z transform is applicable for any kind of functions. Only thing is z transform exists for specific values of z, and that value of z is called as region of convergence. We will see what is the advantage of having all these things in the next video. Okay, yeah, thank you.